Padal and Adashri from Telangana Social Welfare Residential Schools, Center of Excellence, Chitkal, Sangareddy District. Today, I want to share my yesterday's experience with you. Yesterday, when I woke at 8:30, don't think I'm lazy, as this is a pandemic period and lockdown period. As we all became more lazy, I'm one of them. So, when I woke at 8:30, my mom asked me to bring a few eggs from a shop. She gave me 20 rupees. This job, I put on my mask and I took a sanitizer with me for my safety. So I went on the way. The distance is of half kilometer. When I reached half distance, I observed a poster on the wall. The poster is about advances in technology nowadays. And the poster explains how students are showing interest in robotic engineering nowadays. I'm shocked. What's going on, by the way? Why are you showing much interest in that? Is there anything special? These things are going in my mind until I reach shop. When I reach shop, I asked shopkeeper uncle to give me 20 rupees eggs. He gave me 4 eggs and he said each egg costs 5 rupees. 4 into 5 gives 20. Hence, the calculation is verified in my mind. But those things which I observed on poster still going in my mind. And when I am returning to my home, when I looked at my watch, it's about 9:45. The time after 10 will be considered as a lockdown period. So, I need to hurry up as fast as I can. So, I need to run home. I went on the way as fast as I can within 15 minutes. When I reached home, I made a call to my friend. We discussed about why the students are showing interest in robotical engineering. Why it is special from other branches. We discussed much more about it, and that conversation inspired me to choose robotic engineering in future. I think you got the point. What is this time? I said about 9:45 before. What is that? And what is this 20 rupees? And what is this speed? And what do you mean by all these? These are nothing but applications of maths. Maths is of several branches. One of the interesting branch of mathematics is linear algebra. Linear algebra is a branch of mathematics which involves and deals with the linear equations and its concerning and their representation in vector spaces and row matrices. Linear algebra is almost central to all branches of mathematics. One of the interesting topics which has been adapted from linear algebra is robotics. Yesterday evening, I got a call from my friend. She said to me to watch Roboto movie in Zee Telugu. As we discussed yesterday morning about robotic engineering, I showed much interest to watch that movie. That movie is all about Rajnikant sir and Akshay Kumar's equation. I'm a big fan of Rajnikant sir. I watched the entire movie with anxiety. I said, wow, have a robot walks like a normal human being? How it releases bullets through its body? I think you answered me that it's all through graphics. But if we apply all those in all the robotic properties in general applications, we can make it possible. observed everything in that movie with a deep concern. That was a very, very, very interesting one. I'm saying about robotics. Actually, what is robotics? Robotics is a branch of mathematics and it is also a branch of engineering which deals with the conception, design, manufacture and structure of a robot. Robotic engineering overlaps electronics, computer science, nanotechnology, mechatronics, and bioengineering. Nowadays, robotics became an interesting subject. Its structure itself shows how complicated it is. Almost robotics is central to all the engineering area. Many of the students are showing much interest in that. This is what the robotics impact on our present society and present generation. In robotics, the orientation of robotic system can be represented mathematically using rotation matrix. I think you got the point. Today, our main course, rotation matrix. Rotation matrix is a single word. Let's divide it. One is rotation and another one is matrix. What is rotation? Yes, you are right. Rotation is nothing but an act or process turning around a center. Let's take the point where I am standing as center and making a turn or making a round around it is called as rotation. And let's take a live example of rotation. Let's consider our Earth. At the center, our Earth takes itself as a center and rotates itself to complete 1 day or 24 hours. This is one of the live example of rotation. What is matrix? Matrix is a rectangular or square arrangement of elements with fixed number of rows and columns. And all elements present in the matrix must be real. Let's take an example here. Here is a matrix. Horizontal representations are generally called as rows. Vertical representations are generally called as columns. Here we have 1, 2, 3. 3 rows. And 1, 2, 3. 3 columns. Generally, the order of matrix is represented as M cross N. M indicates the number of rows. N indicates the number of columns. Here we have 3 rows and 3 columns. The order of this matrix is 3 cross 3. Let's discuss about the element notation in a matrix. General element notation in a matrix is Aij, where I represents in which row the element is present. G represents in which column the element is present. Let's take the first element. It is present in first row, first column. A general element representation or notation is A11. And let's discuss about second element. It is present in first row, second column. Element representation or notation is A12. This is how a general matrix looks like. We discussed about what is rotation. Now, I just want to take a Cartesian plane here. I took y-axis, x-axis. Its convergence at origin. I rotated this coordinate axis by taking some angle theta. I made a rotation. This is how generally rotation takes place in a Cartesian plane. And then after, I took a cuboid structure. I placed that on my table in my room. I placed an interesting object which is of light green color, which is in the shape of half moon. It looks interesting. To make my room more bright, I placed that in my room. After going so far, when I observed it, I thought that that position is not correct. I want to change its position. I placed it somewhere else. Then again I observed after going to some distance. That looks quite peculiar from before. I'm confused. What happened to this? Any magical movement taken place? What happened to my object? Why its structure looks quite different from before? I'm confused and bewildered about it. One of my friends made me a call. I said her about this. She suggested me to put that in a Cartesian plane. She said that there may be an angle difference. That's the reason it's looking quite different from before. So, I placed an object in a Cartesian plane which has been made by my own self. And again, I shifted its position to somewhere else. By using scales, I measured the angle. And the angle difference is 60 degrees. Oh, I didn't even thought to change the angle. But when I change the position in the system itself, the angle has been changed. That's what happened. Without any thought, we are changing the position of objects from here and there. But there may be an angle difference for sure. That makes the object to look quite different from before's position. We discussed about coordinate axis rotation. We discussed about object rotation. I want to replace the object with a matrix. What happens to it? This is what the main course is. Our main topic, rotation matrix. We discussed about what is rotation and what is matrix. Let's merge both of them. The main course, rotation matrix. In linear algebra, rotation matrix is a transformation matrix which performs rotation in a Euclidean space. Don't get confused about what a Euclidean space is. Generally, Cartesian plane is called as Euclidean space. Why do we call Cartesian plane as Euclidean space? I'll explain you why do we call that. Cartesian plane is a part of coordinate geometry, and Euclid is known as father of coordinate geometry. That's why we call the space surrounded by a Cartesian plane as Euclidean space. For example, here is a rotation matrix: cos theta, sin theta minus sin theta, cos theta. If I place this matrix in a rotation in a Cartesian plane and I made a rotation of it by taking some angle theta with respect to x-axis as origin fixed in a two-dimensional Cartesian coordinate system, what happens to that matrix? In two dimensions, the standard rotation in matrix has been in the following form, which I said before. I want to find the new coordinates formed after the rotation of this matrix. Let the new coordinates be x dash, y dash. They are obtained by general matrix multiplication of matrix cos theta, sin theta minus sin theta, cos theta into x, y. By general matrix multiplication, x dash is equals to x cos theta minus y sin theta, y dash is equal equals to x sin theta plus y cos theta. To make it more clear for you, I want to replace theta with few angles. I want to replace theta with 90 degrees. What happens to the matrix required to be multiplied? Here is a trick here. Don't get confused. In the case of 90 degrees angle, counterclockwise rotation is quite different from the clockwise rotation. In the case of clockwise rotation, the columns reverse. In the case of clockwise rotation, the rows reverse. When it comes to the theta is equals to 180 degrees, in the both cases, counterclockwise case and clockwise case, the matrix required to be multiplied is same. If the theta is about 270 degrees, in this case, the clockwise rotation and anti-clockwise rotation will differ from each other, and the same thing applies. Rows reverse, columns reverse. This is how the matrix rotation takes place in a two-dimension standard rotation matrix. Let's come to an imagination again. Let's take a robot with a parachute bringing, or let's take a spaceship with a parachute bringing the properties of rotation matrix to our Earth. How interesting it is. Robotics is all of these properties of rotation matrix. Every application of robotics must depend on these properties of rotation matrix. Properties of rotation matrix. Let's discuss about it. First important property. Every rotation matrix must be a square matrix. What do you mean by square matrix? You are right. In any matrix, if the number of rows is equal to number of columns, then it is said to be a square matrix. Okay, let's take an example here. Here is a matrix A. It is of order 2 cross 2. Here, the number of rows is 2. Number of columns is 2. They both are same. Hence, it is a square matrix. Here is another example here. Here, the number of rows are 1, 2, 3. Number of columns 1, 2, 3. We have 3 rows, 3 columns. Hence, the number of rows is equal to number of columns. Hence, it is a square matrix. And the other examples are of 4 cross 4, 5 cross 5, and so on. General notation of its order is n cross n. All elements present in a matrix must be real numbers. That implies they include rational numbers and irrational numbers, but they doesn't include any complex numbers. That's what a real number is. And the next property. Every rotation matrix must be an orthogonal matrix. Orthogonal sounds good, right? Orthogonal line is quite peculiar from orthogonal matrix. This property is a very interesting one. You feel like, wow, what is this? Orthogonal matrix is nothing but R transpose is equals to R inverse, where R is the rotation matrix. R transpose means nothing but reversing of rows and columns. R inverse is nothing but adjoint by the determinant. Orthogonal matrix satisfies a property R transpose is equals to R inverse. Here is an example of orthogonal matrix. Here is a 3 cross 3 matrix. If we find the inverse of I, then it is also equals to its transpose. This is what the orthogonal property satisfies. The next property, every matrix has its own determinant. Every rotation matrix determinant may be either +1 or -1. If its determinant is +1, then it shows a proper rotation, like making a proper turn, which means making a clockwise rotation. If the determinant is of -1, then it shows improper rotation, or it is also called as rotor reflection, which means making a improper turn or rotating in a counterclockwise direction. Let's take an example here. The example of proper rotation. Let R be iota square 0, 0, iota square. Iota square into iota square. This is what the determinant of the matrix is. We already know iota square is equals to -1. Iota square into iota square. -1 of -1 gives +1. Hence, this shows a proper rotation, which means rotates in a clockwise direction. Clockwise direction. If, let's take another matrix here. Let R be iota square 0. Determinant is iota square into minus iota square. We know iota square is equals to -1. -1 of -1 of -1 gives -1. Hence, its determinant is -1. It shows improper rotation, or it is also called as rotor reflection. And the next property, the interesting one. For odd-ordered rotation matrix and the eigenvalue, any one of the eigenvalue is unique. Don't get confused about what an eigenvalue is. Let X be an eigenvector which has been picked from a square matrix A. If this satisfies X is equals to Kx, where K be some real value, then K is called as eigenvalue. We can pick up many eigenvalues through a single square matrix by picking up different vectors. And the other property, last but not the least, the trace of rotation matrix is equal to sum of its eigenvalues. I already said eigenvalues. We can pick up many eigenvalues through a single vector. Eigenvalue which has been picked through a single matrix, if we add up all those, then it is equals to trace. What is trace? Trace is nothing but if you pick up principal diagonal elements. Principal diagonal is nothing but if the elements where they are positioning, which means in which row they are present and in which column they are present, if they both are same, then those elements are called as principal diagonal elements. If you add up all those, that is called as trace of matrix. The trace of matrix is equals to the sum of all eigenvalues. This is what the last application is. We discussed many about the robotic system and rotation matrix. And we also discussed few applications of mathematics. This all indicates wherever you go, math follows. In this way, everything and every property of rotation matrix impacts the robotic engineering. We discussed more, right? I want to revise of all those. First, we discussed about what the linear algebra is. Then after we discussed about an interesting topic which has been extracted from linear algebra. Then after we discussed about general rotation in a coordinate axis and a rotation of object in a cuboid structure. We discussed about what is rotation and what is matrix and their convergence rotation matrix. Then after we discussed about a rotation matrix. When we place a matrix in a 2D Cartesian plane, when we make a rotation of it, what happens to it? And their angle differences. Then after we discuss interesting properties of rotation matrix. First thing, let's make a quick revision of those. First thing, every rotation matrix must be a square matrix. Elements present in the rotation matrix must be real. Every rotation matrix must be an orthogonal matrix which satisfies R transpose is equals to R inverse. The determinant of the rotation matrix must be either +1 or -1. If it is of +1, it performs proper rotation. If it is of -1, it performs improper rotation or rotoreflexion. For all ordered rotation matrix, any one of the eigenvalues equals to unity. Eigenvalue is nothing but if I pick up a vector x from a square matrix, then it satisfies Ax is equals to Kx, where K is some real value. Then K is generally called as eigenvalue. And the last property, the trace of the rotation matrix must be equals to the sum of eigenvalues. This is what we discussed before. Any questions to raise?
Thank you, Nageshri. So I would like to ask you that what will be the inverse of rotation matrix?
The inverse of rotation matrix is the transpose of the matrix which is also a rotation.
Okay, then what will be the product of two rotation matrices?
The product of rotation matrix is itself a rotation matrix.
Okay, thank you. And also, are there any geometrical conditions that are, that makes to be satisfied to call a matrix as a rotational matrix?
And in generally, rotation matrix is quite different and they differ from general isometries with two additional properties. The first thing, they leave at least a 1.6. They leave handedness unchanged. Every rotation matrix is a square matrix with all real numbers. It is also characterized as an orthogonal matrix. Then the rotation matrix operates on the vector, on the adjacent vectors to give a rotated vectors.
Yes, okay. Thank you, Nagashri. We are done.
Thank you. I would like to thank our beloved Secretary Sir R.S. Praveen Kumar Sir, RCO Sir, our Principal Madam Pramoda Madam, and my mentor teacher Ramadevi Madam, and my parents for supporting me here. And there are two people behind the screen who are making this program successful, even though it is a pandemic situation. So I would like to thank Shrija ma'am and Sharma sir for giving me this opportunity. To make your learning more effective and interesting in this pandemic, please subscribe our TSWRS channel. Thank you everyone.